Okay, this question is using um, this formula here, which is the just definition basically of an exponential. In class, we've been using like lowercase a for your base. I'm just going to use b for our base here, just to maybe see some comparisons that we know about other functions. If you guys remember back to, we did this with quadratic functions. We've done it with maybe rational functions and um, root functions, all that kind of stuff. But we've got p. Let's say we have a polynomial function of x minus 2, x plus 5. And we know that that polynomial function has roots of 2 and negative 5. It has those zeros. But there is an infinite number of parabolas that go through those points. For instance, if we have 2 there and negative 5 there, we could have a polynomial that, or a quadratic that goes through like that. We could have one that's maybe a little steeper, kind of like that, a little bit dips down further. But we can also have some that are maybe, having those zeros but a little bit shallower. And to find the precise one, the one that we're really interested in, we need another point off the curve, and that other point would allow us to find that a. Okay, so that a, that multiplier, that value that stretches or shrinks a function exists basically in all of our functions. That transformation exists in any type of thing that we do. So over here, it is also something that exists inside exponentials. So a times b to the x. And that's why I used b as my base instead of a, just to show that comparison that that a there is the same as the a when we dealt with stretching or shrinking other functions. So this is how we kind of approach this problem. If we know that this is kind of the foundation, the template for an exponential, we should be able to create from this information up here an equation that models this. Whenever you see the phrase like doubles or triples or something like that, the concept is that we're looking at exponential. Okay, so that's kind of the nuts and bolts of the concept. Now let's get into kind of dealing with this. In order to do this, we need some ordered pairs. And right here, they give us our first ordered pair. They tell us at time 0, your initial population, you have 380 mice. Okay, so that's one x value and one y value. Okay, x and y. Or maybe we call it x and amount at time x, which again, we know that's a y value. The next thing is, okay, now we need something else. We need another ordered pair. Well, they're saying it's doubling every year. So if this is my year, this is going to become 1. Okay. So if in year 0 we have 380 mice, but after year 1 we should have 760 mice. So that is another x or a of x or y. Okay, so now coming down to the formula, basically what we're going to do here is use a system of equations. We're going to go a of x is equal to a times b raised to the x in this, using this ordered pair, and then we'll do the same thing using the black ordered pair. So a times b to the x here, and just fill in the parts that we know. So I'm going to go 380 is equal to, now I don't know a, I don't know b, but I know x is 0. Okay, and now what's really nice about that, what is b to the 0? B to the 0 is 1, right? So I've got 380 times a, or equal to a, times 1. So a, my a value for this particular question is 380. Okay, that's my multiplier. Now I still got to find my base. So I'm going to come over here and I'm going to say 760. That's my a of x is equal to a. Well, a we now know to be 380 mice, times then b. I don't know b, but in this case I do know x is 1. So plugging that stuff in, we get 760 is equal to 380 times b. Well, then b has to be 2. Okay, so now if a is 380, b is 2, we now have the ability to rewrite our function as a of x is equal to 380, that's my a value, times b, so times 2 raised to the x. Okay. The only thing you gotta be careful with here is not to, because these would not be the same, because this is exponential, so we have to leave it as 380 times this quantity. Some people want to write, well, let's just make it 760 raised to the x. You cannot do that. It would not provide you the same results just because of our order of operations. Okay, so maybe that's the best way to kind of visualize this. Now, I did make a slight kind of notation error here. They say use t years. I used x years. So when you type this into your WebAssign, you're going to want to write a of t is equal to 380 times 2 to the t. And then I think the next portion of that question says, okay, what happened? What is the population after then 5 years or 10 years? And then whatever that number is, you just simply replace that t, type it in your calculator, and you get your quantity. Hopefully that helps. If you guys have any more questions, please let me know.